Okay. So if y'all remember the presentation I gave about quantum mechanics, it talked about light being a quantum mechanical property, that it travels as a wave until it's measured, and then it resolves to a particle, and it's somewhere on that wave that's going to resolve. One of the things that it wasn't obvious when we talked about that is, we always talked, because we were looking at the bars, we were looking at sort of a horizontal alignment. But notice that there were actually things that resolved above and down too. Like that wave isn't just going horizontally, it's also going vertically and at all angles. And you can see that here as we shine a light on the back wall. The majority of the light ends up here, but, oh, and by the way, 40-watt light bulb has 1 vigintillion photons per second. That's 1 with 20 zeros, right? Actually, it may be 21. I don't think I have the right number. It may be 21.
12, 14, 16, 18, 20 up there.
Well, it's 20 up there, but I think it's actually 10 to the power of 20, so that would be 21. I just counted. But the point is, it's a lot, right? And you can see here that, of course, the majority of them are here, but when you know this, when you shine a light on the wall, it actually spreads out. It's a circular motion, right? And you can see that some of those actually resolve down here. It's just less likely to resolve down here. So when you look at that wave hitting the wall, it's most likely to be in the middle, but it's not statistical certainty. It's going to, spread out and have less certainty the further away it gets from the middle. And so, but then, the way we've been talking about that is just a single wave, horizontally polarized, right? Polarization is the direction that the wave is going in. So if you have this right here would be a vertically polarized wave. And if you could see this in a 3D space, if we had this, it would look just like a line to us right now. It would be going through the x-axis. But if we tilted it up, you would see that it would be...
So,
yeah.
lifting this up?
Yeah, exactly. Exactly. If you lifted that up even, then... But the thing is, it is in all different directions, right? That's why it creates the circle. The polarization of that light is in several different directions, all directions. But what's interesting is we know that the space, the location of that photon is a quantum mechanical effect, right? It's a percentage. So is the polarization. Which way it's polarized is also quantum mechanical. It's going to, when it's measured, it's going to do, you could say it's doing a statistical analysis as to where it should show up when it's measured. At least that's how I would, if I was writing a simulation of this, then that's how I would do it. We don't know how the real world actually does it, right? And so the polarization this way. And so I'm going to show, with that knowledge, with the fact that polarization is a quantum mechanical effect, I'm going to show a demonstration of that happening, right? Because the idea is, you see this right here, right? This is film. You'll have sunglasses. Polarized sunglasses are exactly that. They're a film that will let only light of a certain polarization through, and the rest of it blocks out, okay? And so in this case, we have light traveling every second, vigintillion plus, probably even more than that, right? We have all that coming through at all different levels, but going through this on the other end as the light comes through, only polarized vertically or horizontally, if I'm holding it this way, or vertically or horizontally, I don't know for sure, right? But only that much light comes through and it blocks it out, okay? So now let's show a demonstration of the quantum mechanical effects. Let me drop that off. I'm going to stop sharing now, and I'm going to, what do I need to do?
You're probably using this camera already, right? If you undo
Yeah.
spotlight mode, will you then be able to see your own camera?
That's a good question. What should I do, auto? Sidebar? What's this down here? Can I pin this?
There we go.
There we go. So I'm going to actually go back to Spotlight. There we go. Okay, and then now I'm going to take this.
Big cut.
Going to get as close as I can so we can get a good demonstration of it. Okay,
Pretty nice camera. That's pretty solid, man. Yeah.
it's not bad, huh? All right, let's create a light source. There we go, great. So take this polarized filter. This light is coming out, non-polarized, it's going all different directions. You put this in front of it, you can see it gets a little dimmer, right? And now it is only letting either vertically or horizontally polarized light through. Now if I take this one, so remember, when it hits this, this is now a measurement of that light wave. So this is measuring it so it then solidifies both in place and in polarization, okay? So this is a measurement of it, because remember I talked about a measurement being an interaction in our classical space. This is part of our classical space. It is measuring that, and it's resolving both location and polarization. So that's a measurement. So let's add another measurement here. This one right here is another measurement. Now look at that. This is clearly aligned the same way. It doesn't seem to be doing anything extra, right? But if I take it and I rotate it, notice, here, let's see if I can get down here so I don't get in the way. Notice as I'm rotating it, see how it gets darker and darker, right? Now notice, now this is, let's say this one's vertically polarized. I don't know if it's vertical or horizontal, it doesn't matter. Let's say this one's vertically polarized. This one is now horizontally polarized. And so now it makes it much darker, right? Makes it much darker. But you're still getting some light through. Why is that? This is only letting vertical polarization through, right? This one's only letting horizontal, shouldn't block at all, except this isn't only letting vertical polarization through. Because remember, it's statistical, right? This one is letting vertical polarization through, so it filters it out. But as it resolves it, some of it is coming through. Or let's say it resolves vertical polarization this way. But when it measures this way, when it measures horizontal, it actually is letting, it's resolving a few of those horizontally, or yeah, horizontally. When this is only letting vertical through, a few of them are being now measured horizontally when it should only be. It's going to be most likely vertical, right? And less, right? Less and less.
Is it not due just to the quality of the material?
No. There may be some aspect to that. I haven't really looked at the material science behind it, but it's not just that, right? And I'm going to show you exactly why. Because now it gets weird.
Oh no.
Right.
It's gonna get weird here.
So what do you do? Predictions. What do you think is going to happen if I put another one in between? Right. So remember, vertical, horizontal. If it's about the quality of the material, right, then you would think that this is going to make it darker, one way or the other, right?
Sure.
So let's test this out. So I don't know, this is vertical or horizontal. Didn't really make it much darker, if at all, right? And then if I flip it, it didn't make it much darker, right? But watch this. This is where it gets really bizarre.
It makes it lighter.
Whoa. That's interesting.
Do y'all know what's happening there?
Nope.
Isn't that weird?
So it's only leaning in diagonal. So why would that amplify?
It's only vertical this way, except, again, it's measured at vertical here. So when it hits this next one, it's going to have a percentage of horizontal to vertical, right? It's going to be in between horizontal and vertical. And based on how it's going to show up horizontal and vertical, remember, if we have the second one be, say this is vertical aligned, If the second one's also vertical aligned, the majority of them are going to come through vertically aligned because that's most likely to happen, right? We go down further, it is less likely to happen that it's going to be vertically aligned, so it's blocking them. But at this stage, it is in a superposition of both vertical and horizontal. Remember, at this stage, like if we hit this 45 degrees, let's say, I don't know how much it is, there's a formula, but let's say half of the photons get through at 45 degrees. That might be true. Let's say half of them get through at 45 degrees. So now they're going to be 45 degree aligned. So then when I put this up at a 45 degree angle from that second one, half of those are also going to get through. Actually, did I do that right? So half of those are also going to get through at a 45 degree angle. So it's not about the material, it's about the effect. And notice now that we are dealing with vertical and horizontal here, it's not going to be darker as we go down this way as well, because it's aligning. So the best place is when half of the photons in the second measurement at a 45 degree angle are getting through, whereas in this case it's actually blocking a majority of them.
So is it just that it switches polarization almost between the first lens and the second lens? Like that it starts as vertical and between that tiny little space there's a small proportion of these photons that are switching polarization?
No, it's not a small portion. I mean, when we talk about polarization, remember it's probability, right? So this is actually sending all vertically aligned particles through, right? Light particles through. All vertically aligned light waves are coming through this way, right? And when you now do another measurement, you're going to have a chance of measuring those as being vertical because they were vertical back here. There's going to be a high chance of those being measured as vertical, a very low chance of those being measured as horizontal.
And since it's not a sudden shift, it's a gradual shift, does that mean it's a higher probability that they're closer to vertical than horizontal? Yeah.
Notice it does do gradual. There's the highest probability here that they're going to come through the second measurement vertical, and then less and less and less and less and less and less all the way through.
Does that change if you like put more space between the two lenses?
The answer is yes, but not materially so for our world.
Gotcha.
But yeah, I mean that would have some effect because the further away the measurement is, the wider out spread the wave itself is. I don't know if that actually affects polarization, the ones that hit it. I mean, there's going to be less that hits it because of that, right? So that would be the only thing that affects it. But that one in between, notice it doesn't do anything on the outside. It has to be in between because, again, what it's doing, the first one vertical, this one 45 degree, so that when we measure it again, so half of the photons are getting through at this stage. You know, very few of them are getting through at this stage, but half are getting through at this stage. But when we do that other measurement, then it's still darker than all the ones that came through, but it's not as dark as just doing horizontal and vertical alignment. Quantum mechanical effects.
If you put it, and so also the bouncing off of a windshield is similar to a filter then, because people wear polarized sunglasses because most light that hits your eyes is bouncing off of surfaces horizontal parallel to the ground, and so those lights don't go in your sunglasses, right? So bouncing off, like if you look at like a window or of a car, you know, and you can't see it because it's reflected, but if you put on polar glasses and go like this, then it's see through, and if you go like this, then it's shiny again.
Yeah, so if the windshield is polarized, then that's what would happen, yeah. But bouncing off of the ground doesn't matter.
The windshield is polarized. It's not because it's bouncing off of a surface parallel to the ground.
No, but the actual bouncing off a surface doesn't, I mean, it resolves its polarization, but it doesn't change. It doesn't filter
so fishermen use
things that are polarized a certain way.
Fishermen use it for rivers all the time. That's like my dad polarized glasses for rivers because you can see through the water when you're wearing polarized glasses.
Oh, interesting.
So I wonder if the bounce.
Yeah, I don't know what the science behind that is. That's pretty intriguing. Yeah, I don't know. Water does affect light. I know that. That's all I know. So, anyway, that's all I got.